Magnetic flux. Magnetic flux describes the quantity of magnetic field lines that pass in a perpendicular direction through a given surface area and is represented by flux B equals B perpendicular times A. Phi is the Greek letter phi and stands for flux or flow. Adding the subscript B makes it magnetic flux. Electric flux, of course, would have a subscript of E. The unit of magnetic flux is the Weber, where 1 Weber equals 1 Tesla meter squared. And you can see that right here, right? Magnetic field is Tesla, area is square meter, so it's Tesla meter squared, and it's Weber. Again, named after a famous physicist. Another definition or reuse of something we've already seen in mechanics and electricity. We need the normal. The normal is a line that is perpendicular to a surface. So here's a surface kind of coming out of the board here. And you have a normal that is perpendicular. There's perpendicular to the top side of the surface. And here, coming underneath, is perpendicular to the underside. The magnetic flux would be at a maximum at any point on the surface where it is parallel to the normal. So it gets a little tricky here. I mean, right here as we kind of summarize it, where your magnetic field lines are perpendicular to the surface, it's at a maximum. But when you're perpendicular to the surface, you are parallel to the normal. And normal is a very handy concept, and we'll use that more than we do surface. So we've defined magnetic flux and shown where it's a maximum and where it's a minimum. So let's get back to the guy whose name we took as units. Wilhelm Eduard Weber was a German professor and physicist who stressed the importance of experiments for students learning physics. He also worked and published with Carl Friedrich Gauss, and together they developed the first electromagnetic telegraph. However, he started getting into politics here, which is never a good idea for a physicist, and he lost one of his university teaching positions as he was doing politics against the King of Hanover. He should have stuck with physics. Here's our surface, this yellow surface here. Here's the normal lines, that one going up, that one coming down. And we have magnetic field lines. We have a magnetic field that is perpendicular to the plane of the loop of wire, this orange surface here, and parallel to the normal, the two normals. See how they're parallel here? Therefore, the magnetic flux is at a maximum and is equal to the strength of the magnetic field times the area of this loop. Again, here's our surface or loop of wire. The two normal lines are drawn, one below, one above, and we have a magnetic field that is parallel to the plane of the loop of wire, and it is perpendicular to the normal. So the magnetic flux is at a minimum, and this time the flux is 0. An easy way to look at that is if there are no magnetic field lines going through the plane of the loop of wire, then there's 0 flux. It's a little tricky to see here, but they're just bypassing the plane. Nobody's going through the plane, so you have 0 flux. The magnetic flux is proportional to the total number of magnetic field lines passing through a loop. Let's take 3 cases here. We've actually already done this case and this case, but we want to go intermediate. Here, the magnetic field is perpendicular to the normal. Here's the surface we're talking about here. Over here, the magnetic field lines are parallel to the normal, and you can see that the angle it makes is 0. We're measuring the angle to the normal. Here it's 90. We know that the flux is 0 in this case, and it's a max here. Here my angle between the normal and the field line, so let me just draw the field line right there. This angle here, you always measure to the normal. That theta is 45 degrees. And oh yeah, I even put that in red just to make sure you can see it. What happens here? What's the flux in this middle position? The magnetic flux is proportional to the total number of magnetic field lines that pass through the loop. So here's our loop, and the magnetic field is going this way, and this line here is the normal. So the magnetic flux is at a minimum when the field lines, which are these, the horizontal ones, make an angle of 90 degrees with the normal. Okay, there's the 90 degrees, here's the normal. So let me just go ahead and erase all that stuff. Physically, no field lines go through the loop, right? Here's the loop, and all the field lines are going right by it, so there's zero flux. The flux increases as the loop is turned, as more field lines pass through the loop. So let's look at this first one. We're at 45 degrees. Got 1 line, 2 line, 3 line, 4 line, and a little bit more. Here, when you go to theta equals 0, 1, 2, 3, 4, 5, 6, so there's more. So the flux is increasing as a loop is turned, as more field lines pass through the loop. It reaches a maximum when the field lines are parallel with the normal. So here's the normal, and here are the field lines parallel. That makes an angle of 0. So you have maximum flux when theta equals 0, minimum when theta equals 90 degrees.